Hi everyone, we're going to do Matrices Day 2 today, and we're going to be focused on the determinant. The determinant is a number that represents the matrix. One number to represent the matrix. All those cells in that matrix, one number to represent the matrix. That's kind of cool. Now, this thing about determinants is we can only find the determinant. There's too many M's there. Mr. Kukla, too many M's, and that's because that's an I-N, determinant. The thing about determinants is you can only find them for square matrices, like a 2 by 2 or a 3 by 3 or a 4 by 4. You can't find a determinant for a 1 by 3 or a 2 by 1 or a 3 by 5. Only for square matrices can we find a determinant. And for 2 by 2, you might have in Algebra 2 seen this. So if you've got A, B, C, D, there's, by the way, notation for this. Here's matrix A, and the notation for find the determinant is, and it looks like absolute value of A. And the way that we can do this, we have a little recipe, which means we take this diagonal product, A times D, and we subtract this diagonal product, B times C. And so if I have 1, 3, 7, 2, then the determinant of, and we'll call that matrix B, the determinant of matrix B is going to be 1 times 2 minus 3 times 7, or 2 minus 21 for negative 19. Negative 19 is the one number that represents that matrix. Okay? So there's that nifty little formula, and it works wonderfully for 2 by 2s. And sometimes the ACT asks about 2 by 2s and the determinant of a 2 by 2. And so it would be good if you were comfortable finding the determinant of a 2 by 2. So here's a 2 by 2. 3, negative 5, 6, negative 8. Will you please find that? Okay, pause the video, give it a go. Welcome back. So we know it's this diagonal product, negative 24. In fact, I'm going to write it out, 3 times negative 8. And then we're supposed to subtract this diagonal product, negative 5 times 6. We've got negative 24 minus negative 30, which is negative 24 plus 30, or positive 6. Okay, so we can find the determinant of a 2 by 2. Now, we can also find the determinant of a 3 by 3. However, things get a little more challenging with a 3 by 3. So, for example, if I have 0, 3, 4, 2, negative 1, 0, 1, 2, 1. I can't just use this and this. That does not work. Instead, what I have to do is I can still do that diagonals approach, but it gets modified for a 3 by 3. And oh, by the way, the diagonals approach does not work for a 4 by 4. So I'm also going to show you 2 other ways to find the determinant. Okay, so we had 0, 3, 4, 2, negative 1, 0, 1, 2, 1. Okay, so diagonals. Well, I do agree that I have this main diagonal here. But I've also got this diagonal, which continues here. And I've got this diagonal that continues here. And some students find it really hard to live in that sort of wraparound universe where these two go with this one and this one goes with these two. And so what most math teachers say is the first thing you should do before you even start circling bits, in fact, I'm just going to write it over again, is that you should copy the first two columns again. So we have 0, 3, 4, 2, -1, 0, 1, 2, 1. And copy these first two columns and put them over here. 0, 3, 4, 2, -1, 0. Okay, now, by moving these two over here, we don't have to worry about wraparound. We've got those, we've got those, we've got those. We also have these, and these. Okay, so diagonal product method. Let's think about these diagonal products. Here, we're going to have 0 times -1 times 1 plus 2 times 2 times 4 plus 1 times 3 times 0. And so I end up with 0, 16, and 0. Okay, and what about this set of diagonal products? Well, 4 times -1 times 1 plus 0 times 2 times 0 plus 1 times 3 times 2. And so I end up with -4 plus 0 is -4 plus 6 is 2. But wait, remember when we did the 2 by 2, it was this diagonal product minus this diagonal product. Well, now we have to do this sum of these diagonal products minus the sum of these diagonal products. So we end up with 14. Our determinant here is 14. Okay, so we should probably do one more of those, huh? Okay, let's do one more. Here we go. Whew. Here's our matrix. -5, 4, 1, 3, -2, 7. Bottom row is 2, 0, 6. Okay. So the first thing I want to do is, and again, here's matrix A. I want the determinant of A, which means I'm going to do -5, 3, 2, 4, -2, 0, 1, 7, 6. Copy those first two columns, -5, 3, 2, 4, -2, 0. Okay, and I want my diagonal products. So I've got this diagonal, and this diagonal, and this diagonal. -5 times -2 is positive 10 times 6 is 60. 28 times 2 is 56. And 1 times 3 times 0 is 0. And so I have 116 that way. And then I want to subtract from that this diagonal product plus this diagonal product plus this diagonal product. And so I'm going to have -4, I'm going to have 0, and 12 times 6 is 72. And so we're going to subtract, and it has to be this diagonal sum minus this diagonal sum. Can't be the other way around. We're going to subtract, and we end up with 48. Is it 48? Suddenly, I'm concerned, because this is 28 plus 16, 44. I should get 44 there. Did I make a mistake? Let's check. 60, 28 times 2, and 0. Okay, and, yeah, and then here, negative 4, 0, and 12 times 6. 12 times 6 is 72. Yes, 72. So this is, there it is. I forgot to subtract the 4 there. So that's 68. Okay. And so we end up with 48. The determinant of A is 48. Okay. Now, we can also, because this 3 by 3 method, I guess you need practice with it. So here, you do this one. 2, 7, negative 3, 1, 0, positive 4, 4, negative 1, negative 2. Here's matrix A. Please find this. Okay, pause the video. Go find it. Okay, welcome back. So, using the diagonals method, I've got 2, 1, 4, 7, 0, negative 1, negative 3, 4, negative 2, 2, 1, 4, 7, 0, negative 1. And I want diagonal products. So there's diagonal product, and there's diagonal product, and there's diagonal product. So that's 0. This is 28 times 2. I'm sorry, times 2 would be 56. So I get 112. So this is 0 plus 112, and that's plus 3. So that's 115 going that way. And now what about the other diagonal products? The sum of these diagonal products. And I get negative 12. That's a 2, a 4 is 8, times negative 1 is negative 8. And then we have a negative 14. So I've got negative 26, negative 34. And remember, what we want to do here is we want to subtract. I want to subtract these two. So I'm doing 115 minus a minus 34, which gives me 149. I have a different number in my notes, so I'm going to check to make sure I copied down the same matrix. 4, negative 1, negative 2. Now I'm going to look for my mistake. Yes. 3, 4, negative 2, 2, 1, 4, 7, 0, negative 1. Okay, that's 0. 28 times 4, or 7 times 16, is 112. And then we've got positive 3 for positive 115. I like that one. This is 0. There. So that's not that. That's 22. Negative 22. Let's make it in green so we're consistent. Negative 22. 22, which brings me to positive 137. Okay, watch out for small mistakes when finding the determinant. But if I ask you to find the determinant of this 4 by 4, 3, negative 1, 2, 0, 4, 0, negative 3, 5, 0, 6, 0, 0, 1, 1, 1, 3, negative 4, 2. So here's our matrix A, and I want to find the determinant of A. I can't use diagonals method. Sad face. So, conveniently, people a couple hundred years ago came up with this interesting approach called minors and cofactors. Let's go through a problem that we've already done, and I'll show you how to do it using the process of expanding along a row or column using minors and cofactors. 0, 2, 1, 3, negative 1, 2, 4, 0, 1. Here's matrix A. And we already found the determinant of this and found it to be 14 using the diagonals method. So I'm going to teach you how to use minors and cofactors now. And it works like this. First, I don't have to rewrite the second column, the first two columns over here again. Okay? What I do need to consider is expand along any row or column. And I'm actually going to do this a couple of times with this matrix. And the reason we know the determinant is a number that represents this matrix is regardless of which row or which column I expand along, I am always going to get the same number. This number, no matter which row or column I expand along, will always be the same. So I'm going to start by expanding along this row. Why? Well, it's the first one I saw. Why? Because it had a 0 in it, and that's going to make my life easier. So here's how it works. 0 times, that's this number, goes here, times the determinant of, now choosing this number for here cancels out, it's in this row and it's in this column. And so we just have this little 2 by 2 down here, negative 1, 2, 0, 1. Plus, now I come over to the 2, and the 2 cancels out this row and this column, so I'm left with 3, 2, 4, 1. 3, 2, 4, 1. And then finally we have this 1. And so that's going to cancel out that row and that column, which leaves me with 3, negative 1, 4, 0. 3, negative 1, 4, 0. Now, when I go through and find each of these little determinants, those are called minors because they're the minor determinants. So here I have negative 1 minus 0, which is negative 1. And then I have 3 minus 8, which is negative 5. And then I have 0 minus a minus 4, which is 4. Right? Because minus a minus 4. Okay, and so I add these together and I get negative 10 plus 4 is 6. Uh-oh, I'm sad because we already know that the determinant should be 14. Well, you may recall I said minors and cofactors. We're going to use minors and cofactors. And what was determined was that just finding these minors wasn't enough. I had to overlay on top of this a magical cofactor fabric. For a 2 by 2, the cofactor fabric looks like this. For a 3 by 3, the cofactor fabric looks like this. For a 4 by 4, it looks like this. And so we can see these, the cofactor fabric, because we can only find determinants in squares. Cofactor fabric always comes in square shapes. It's either 3 by 3 or 4 by 4, and the signs always alternate, and we always start with a plus in the top left corner. Now, how do we use this cofactor fabric? Well, we expand it along the top row. So when I look at the top row, I see plus, minus, plus, which means I'm supposed to multiply this answer by a positive I'm supposed to multiply this answer, this minor, by a negative, so times by negative, and I'm supposed to multiply this one by a positive. So then I have 0 plus 10 plus 4, and I get 14. Okay, so when I combine minors and cofactors, I can get the correct determinant. Now, we expanded along the top row. What about expanding along the middle column? So that's going to be 2 times this 2 cancels out this column and this row, leaving me with 3, 2, 4, 1, 3, 2, 4, 1, plus a negative 1. That negative 1 takes out this column and this row, leaving me 0, 1, 4, 1. And then we have 0 times this knocks out this column and this row, 0, 3, 1, 2. Now the nice thing about choosing the row or column with the most zeros in it is I don't really have to bother to find this minor because that minor times 0 is just going to be 0. So I'm just going to do this one, 3 minus 8 is negative 5, minus 1 times 0 minus 4, plus 0 times 0 minus 3, negative 3. All right, and now don't forget the cofactor fabric. We're doing this column, which is minus plus minus. So I want to multiply this by a negative. I want to multiply this by a positive. I want to multiply this by a negative. So I've got negative 10 times negative, which is positive 10, plus 4 times a positive 4, plus 0 is again 14. Regardless of which way, which row, or which column I use to expand along, I can always get the same determinant. And that's what's really powerful about this, well, one, that there can in fact exist a determinant for a matrix, because regardless of which way I go, I get the same number every single time. But this method of minors and cofactors and expanding along a row could work with 4x4s and 5x5s and 6x6s. It's much more time consuming, and so I'm not really going to dwell into it, especially since, ta-da, welcome to our friend calculator. So with the calculator, we can actually find the determinant. So let's type in this determinant again. Matrix, edit. This time I want a 3x3. And so we've got 0, 2, 1, 3, negative 1, 2, 4, 0, 1. And then I quit and I go back to matrix. And this time when I go over to math, look here, the very first choice is det. That stands for determinant. And now the calculator is saying, well, what do you want to take the determinant of? And we want to take the determinant of matrix A. So we go back to matrix a third time, and we just choose the name this time. And so we have det A, enter, and there's our 14. So I could use minors and cofactors to find the determinant for 3, negative 1, 2, 0, 4, 0, negative 3, 5, 0, 6, 0, 0, 1, 3, negative 4, 2. In fact, let's expand along this row, because it's pretty straightforward. In fact, let's not expand along that row first. Let's expand along the top row first, or even this bottom row. So 1 times, and now that cancels out this and this, leaving me negative 1, 2, 0, 0, negative 3, 5, 6, 0, 0, plus 3, and that knocks out this and this, leaving me 3, 4, 0, 2, negative 3, 0, 0, 5, 0, And then we've got negative 4. Negative 4 knocks out this and this, leaving me 3, 4, 0, negative 1, 0, 6, 0, 5, 0. And finally, we've got 2 times, that knocks out this and this, leaving me these 9, 3, negative 1, 2, 4, 0, negative 3, and 0, 6, 0. Yes. Okay, so, but look, I still have a 3 by 3, and so now I'd have to expand along a row or column here, and 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 that's going to be an awful lot of work, because then I still have to multiply by these, and I still have to remember the cofactor fabric, not just on the 3 by 3, but also the cofactor fabric for the 4 by 4. So double cofactor fabric. So that's a lot of pain in the butt work, and that's why I strongly would recommend, if you had to do something like this by hand with minors and cofactors, that you go for the row with the most zeros. And so we would just have 6 times, because that would knock out this and this, 3, 4, 0, and then 2, negative 3, negative 4, 0, 5, 0. Okay, because these will all be 0 times stuff, and so I really don't have to worry about any of these other parts of the determinant. So what could we do here? Well, if we expand along this top row, we're going to say, don't lose that 6, by the way. So we've got 3 times, knocks out these, negative 3, 5, negative 4, 2, plus the 2 times, knocks out this and this, 4, 5, 0, 2, plus 0 times stuff, and I'm not really worried about that stuff. And these are determinants, so no brackets. 0 times 4, negative 3, 0, negative 4. Okay, so here I have negative 6 minus a minus 20 is 14. And here I have 2 times 8 minus 0. And here I have 0 times stuff, so I don't really care because that's going to be 0. But we expanded along the top row, so I have to multiply by positive, by negative, by positive. So this times a positive, this times a negative, so I have negative 16, and a plus 42, and plus 0. So that's going to be 26. However, I still need to multiply by this 6, right? But wait, that 6 is in this 4 by 4, and it is in the 1, 2, 3rd row, 2nd column. So we've got, I didn't finish this one, I did, so we're down 3 and over 2. 1, 2, 3, over 2. So I actually have to multiply by negative 6. So negative 6 times 26, and we end up with negative 156. I think so. Now I got negative 216 when I did it before. So clearly I've made a mistake in here somewhere, and that doesn't surprise me. I seem to make a lot of those with this today. So we've got negative 6 minus a minus 20, positive 14, and we've got positive 8 minus 0, and I don't care what this is because it's times 0. And then I've got my cofactor fabric for the top row, plus, minus, plus. So that's going to be negative 16, positive 42, and a positive 0. And so 16, 42 minus 16 is in fact 26. Like that. And I'm supposed to multiply that by negative 6. So times negative 6 equals negative 156. Well, you know what? I can check with my calculator by typing in the 4 by 4 matrix and seeing if I in fact have made a mistake. So let's go to matrix and let's go to matrix and edit. This time a 4 by 4. we've got 3, negative 1, 2, 0, 4, 0, negative 3, 5, 0, 6, 0, 0, and finally 1, 3, negative 4, 2. Okay, and then we'll go back to matrix, but this time we go to determinant, and we want to do the determinant for matrix A. And see, I do get negative 216. So, somewhere along the way in here, I've made a mistake now twice. 6, 3, 4, 1, 3, 4, 1, that's a 1. That's where the mistake was, at the very beginning. Oh, that's horrible. 3, 4, 1, 2, negative 3, negative 4, 0, 5, 2, nice. And so then, when I did 3, these are correct. When I did 2, 4, 1, that should be a 1. And so now I'm getting 8 minus 5, which is 3. And then with this last one, I have 4, 1, but it's still times 0. So that shouldn't matter. And this is now made this minus 6, which is 36, and 36 times negative 6 equals negative 216. Ta-da! Okay, so that's finding the determinant. In our next video, and I will say this, I'm all happy to use the calculator to find the determinant. Great. Solve systems with the calculator, use the calculator to find the determinant, all good by me. But I do want to take a moment to be really freaking impressed that someone figured out how to use minors and cofactors to figure out the determinant for a 3x3 or 4x4 or even a 5x5 matrix. I find it pretty damn impressive that in the 16 and 1700s people could come up with this. By the mid-1700s, we had Gabriel Kramer coming up with a way to use determinants to solve systems of equations. And we'll take a look at that in our next and last matrix video.